Welcome to this explainer on the hidden physics and infrastructure that absolutely make or break high-speed rail. When we think of high-speed trains, we usually picture that sleek, aerodynamic nose of the train itself, right? But honestly, the true engineering marvel isn't just the train. It's the incredibly precise mathematical geometry of the steel tracks right beneath it. Today, we're diving straight into the fundamental physics of track design. We're going to translate some pretty complex engineering data and uncover the literal foundation of 300 km/h travel. Here's a quick look at our roadmap. We'll tackle the high-speed gauge dilemma, break down the physics of Cant and Cant deficiency, zoom out to look at curves and gradients, and then wrap up with India's unique broad gauge blueprint. All right, let's jump straight into part one, the high-speed gauge dilemma. So we have to start with the absolute foundation of any railway, which is the gauge. That's just the distance between the two interfaces of the rails. Historically speaking, pioneers like Japan and France decided their new high-speed trains needed completely new, dedicated lines, so they went with the standard gauge of 1435 millimeters. But India faced a totally different geographic and economic reality. They made this incredibly bold choice to design their high-speed corridors using their existing wider broad gauge, which sits at 1676 millimeters. Why do that? Well, it's all about seamless interoperability. A wider gauge means conventional, heavier express trains can actually share the exact same high-speed infrastructure. And for network utility, that is a massive advantage. Okay, moving on to section 2, the physics of Cant. Once you lay those rails down, how on earth do you get a train to take a corner at 300 km/h without just flying off the tracks? You know that feeling when you drive a car around a sharp corner and your body gets pushed outward? That's centrifugal force. To fight this on a railway, engineers use something called cant, which is also known as superelevation. It's simply the amount the outer rail is raised above the inner rail on a curve. Think of a steeply banked racetrack in motorsports. Cant literally tilts the entire train inward. It's this perfect balancing act of physics that uses the inward tilt to completely counteract the outward centrifugal force, keeping the wheels firmly planted and passengers totally comfortable. Figuring out exactly how high you can tilt to that outer rail isn't guesswork. It requires sheer, absolute mathematical precision. Engineers use highly specific formulas to balance the dynamic gauge, which is the actual functioning width of the track, against the height of the train's center of gravity. Because if you bank the track too much, the train could literally fall over to the inside. These calculations are absolutely crucial to make sure we maximize speed without ever crossing the dangerous threshold of overturning. But here is where we hit a fascinating problem, the stationary train paradox. A track that is steeply banked for a 300 km/h train suddenly becomes a massive overturning risk if a train is forced to stop completely on that exact same curve. Think about it. If the train stops, that outward centrifugal force holding it up vanishes. All of its weight immediately shifts down to the lower inner rail. Add in some high wind pressure blowing toward the inside of the curve or severe ground vibrations, and you've got a recipe for derailment. So engineers don't just design for the fastest moving train, they have to design for the one standing perfectly still. To give you a real sense of the staggering safety margins built into these calculations, just look at this number, 129 km/h. Based on the physics of a stationary train sitting on an optimally canted standard gauge curve of around 3,500 meters, it would take a sustained extreme side wind of 129 km/h to actually tip the coach over to the inside. I mean, that really shows you just how incredibly robust and conservative those maximum cant limits, which are generally capped around 180 to 200 millimeters, really are in practice. So we know we can't overbank the curves. Let's move to part 3 and see what happens when we have to master Cant deficiency. Here's the reality of a mixed-use railway network. You are going to have a super fast passenger train zooming through a curve, and maybe an hour later, a much slower express train takes that same bend. Engineers literally cannot design the perfect equilibrium cant for every single train speed. If they bank the curve purely for the bullet train, the slow train might tip inward, so they have to make a compromise. This compromise forces engineers to rely on what's called Cant deficiency. This happens when the actual physical cant provided on the track is less than what a fast train ideally needs for its absolute top speed. The engineering formulas dictate the strict limits of this deficiency. In practical terms, Cant deficiency creates uncompensated lateral acceleration, which, simply put, is just the mathematical way of describing that sensation you get when you're gently pushed into the side of your seat as the train rounds a bend. Now, we obviously can't just throw passengers hard into the side of the train car. Passenger comfort is absolutely key. Because of that, engineers strictly limit something called lateral jerk. This is the rate of change of that outward acceleration over time. Think of it like a coffee cup test. Engineers cap this lateral jerk at an incredibly smooth 0.02 g per second. This ensures that as your train enters a high-speed curve, your morning coffee doesn't spill a single drop, and you remain perfectly comfortable, completely unaware of the intense physics happening right beneath the floorboards. Let's step back from the microscopic rail geometry for a second. Part 4 is all about designing curves and gradients on a macro scale. Because we have those incredibly strict limits on Cant and Cant Deficiency that we just talked about, you really cannot have sharp turns on a high-speed track. A high-speed broad gauge line requires massive, gentle horizontal curves. Get this, for a train traveling at 350 kilometers per hour, the recommended minimum radius for a curve is a staggering 7,000 meters. That is a curve so incredibly wide and gentle that, to the naked eye, the track almost looks like it's running in a perfectly straight line. Now, moving to the vertical alignment, we run into a totally different type of challenge, gradients, or basically hills. The world takes varying approaches here. European dedicated passenger lines, like the ones in France and Germany, can climb steep grades up to 40 per mil. They use light, incredibly powerful passenger trains that act almost like roller coasters. India, on the other hand, opts for a much, much flatter maximum gradient of 1 in 150, which is roughly 6.6 per mil. The absolutely crucial takeaway here is that India's flatter gradient isn't a limitation, it's a very deliberate strategic choice. By keeping those hills gentle, interoperability is preserved. It guarantees that heavier conventional locomotives pulling standard passenger coaches can safely share this cutting-edge high-speed infrastructure. There's no risk of them stalling out on the way up or burning out their brakes on the descent. So bringing everything we've learned together, let's look at Part 5, India's broad gauge blueprint. This blueprint right here is the ultimate culmination of all that physics. For Indian broad gauge corridors, which are set at that 1676 millimeter width we mentioned, engineers carefully balance a maximum track cant of 200 millimeters with a safe cant deficiency of 100 millimeters. This is the master recipe. It dictates everything from that giant 7,000-meter horizontal curve radius to the careful transition curves that smoothly ease the train from a straightaway right into a bank, and it's all designed for a blistering top speed of 350 kilometers per hour. But writing the numbers down on a blueprint is one thing. Actually building it in the real world is a whole different beast. The massive scale of the civil engineering required here means tunnels, viaducts, and subgrades literally have to be constructed to tolerances measured in millimeters, stretching over hundreds of kilometers of natural terrain. Every single parameter we've discussed today is a precise engineering solution physically carved into the earth to ensure absolute safety and total passenger comfort. We've seen exactly how physics dictates the absolute limits of track geometry and how different countries adapt these universal laws to their own specific needs, whether that's Europe's steep dedicated lines or India's wide, mixed-use broad gauge. And really, it leaves us with one thrilling question to consider. As material science improves and we continue pushing the boundaries of physics and infrastructure, just how much faster can the track of the future take us? Thanks so much for exploring the architecture of speed with us.